Okay, so we saw the integral test and now we're going to apply it on on these examples. So first let me repeat the integral test itself. So step 1 would be to set up what f of x is. I mean, that's pretty easy, straightforward. Then step 2 would be to find the improper integral from 1 to infinity of this function. Now this obviously takes time, and you remember all the steps of improper integrals. That's why we studied improper integrals earlier. So that takes time, and you find what the improper integral is. Now improper integral, as you may remember, could diverge or it could converge, and that's why we had used this phrase diverge and converge at that time also. So now once we come to that conclusion, then we are ready to find what the series is doing. So the series would converge if the integral converges, and it would diverge if the integral diverges. In other words, they go together. You will see this kind of thinking in other tests as well. So whenever I use the phrase they go together, that means if one converges, the other converges. If one diverges, the other diverges. Okay, so let's start with this particular series. So this series is actually n from 1 to infinity, n over n squared plus 3. So step 1 is my f of x, which basically means I'm going to write x where I see n. Step 2, I have to find the integral 1 to infinity x over x squared plus 3 dx. Now you remember how to find the improper integral. So we are going to first break it up as limit b going to infinity 1 to b x over x squared plus 3 dx. Then we will go on the side and find this definite integral. So let's start with finding the simple integral x over x squared plus 3, but you know very well how to find this. It just needs a very simple u substitution. U is x squared plus 3, so du is 2x dx. So you go and substitute and you get du over u, and then you also have a half, and the integral obviously is half ln u, which means half ln x squared plus 3. So this is the first step. Then we put in the limits. So when you go from 1 to b, you're going to get half, let's keep half outside, ln of b squared plus 3 minus ln of 1 squared plus 3. And then finally we're going to take the limit b going to infinity of this. It's a lot of writing, but actually nothing very special happening. So this is ln of 4. Who cares about ln of 4? So what happens when b goes to infinity? Well, this term is obviously going to infinity. So in short, this improper integral is divergent, so it diverges. So if the improper integral diverges, we can conclude that the series that we had started with, that also diverges. So the series an, which was n over n squared plus 3, diverges. Now, I did this example using the integral test. Now remember, I had mentioned that this is usually used when you have transcendental functions or if something else is not working. Now this was a very straightforward series, and we could have come to this conclusion in a very simple test, which you will see very soon. So actually this was an overkill for this particular problem. Now let's go to the next example, and this one says we want to study a series n e raised to the power minus 3n. Now this one has transcendental function, and it would be best to use integral test for this. So first thing is, what is f of x? That would be x e raised to the power minus 3x. So that means I have to find 1 to infinity x e raised to the power minus 3x dx, which means limit b going to infinity 1 to b x e raised to the power minus 3x dx. So this is going to require a simple substitution, because actually this is a typo here. This was n squared. It's not, this is minus 3n squared. So this was x squared, therefore it requires a very simple substitution of u equals minus 3x squared. So du is minus 3x minus 6x dx. So dx is du over minus 6x. So I'm working on this. So this integral becomes x e raised to the power u du over minus 6x. So that is negative 1 over 6 e raised to the power u du. So that gives me e raised to the power minus 3x squared. Now I'll put the limits 1 to b, and that will give me negative 1/6 e raised to the power minus 3b squared minus e raised to the power minus 3. Okay, so now we are ready to take the limit. So limit b going to infinity of that stuff would be, well, as b goes to infinity, this term is going to 0. Therefore, I'm going to be left with negative 1/6 times 0 minus e raised to the power negative 3. So that is e raised to the power minus 3 over 6, which is, a finite number. So therefore, the improper integral converges. So since the series and the improper integral go hand in hand, they go together, we can therefore say that the series an also converges. However, the sum of that series is not this number. So note that series n e raised to the power minus 3n square, that is not equal to e raised to the power minus 3 over 6. The sum is not that, and that is something that we were warned about earlier also. Okay, let's go to the next one. So now we have this series and the function. So step 1, the function is ln x over x. Step 2 is to find 1 to infinity ln x over x dx. So that means limit b going to infinity 1 to b ln x over x dx. So as before, let's start working on this improper integral. So first I would simply integrate ln x over x dx, but this is again an easy integral. I will say u is ln x, so du is dx over x. So very convenient. This becomes u du, so that is u squared over 2, so that is half ln x squared. Okay, so now we can put the limits 1 to b, and when I put the limits, I get half and ln b squared minus ln 1 squared. But this is 0, log of 1 is 0, so I'm just simply left with half ln b squared. So finally, we find limit b going to infinity half ln b squared. But as we know, log goes to infinity, log graph is like that, so that means this is infinity. So that means the improper integral diverges, and therefore the series also diverges. Now this is a pretty useful test for this particular series. It is not very easy to show that this diverges using any other test. So some of these series that we saw can be tested using other tests that we'll see very soon. Now we are ready to define what are called p-series. So these are pretty handy series, very useful. So a series 1 over k raised to the power p is called a P series, and its convergence depends on the value of P. So that means, suppose you have 1 over K, so this is P is 1, so it's a 1 series, which is also called harmonic series. Similarly, we could have 1 over K raised to the power 5 over 2, so this is 5 over 2 series. Now the convergence of all these series, this one or this one, it all depends on the value of P. So it says if P is less than equal to 1, then these series diverge. If P is greater than 1, then it converges. Actually, the proof is very simple, because all that you have to do is use the integral test, and then we have the improper integrals. And if you remember, we had this result 1 to infinity 1 over x raised to the power p. This diverges if p was less than equal to 1, and it converges if p was greater than 1. You can look back in your improper integral notes and you will see that we studied this. So therefore, from the integral test, we have this result for the P series, and this is something important to remember. Okay, next we are going to go over to section 10.5 and study what are called comparison tests.